Welcome back. Today's topic is about the uh, magnetostatics and electromagnetic induction. As we are in the course of electricity, magnetism, and electronics, the second topic is about the magnetostatics and electromagnetic induction. Okay. My name is Prakash, working as a lecturer in the Department of Physics and Electronics in K.B.N college. Okay. Now, coming to the contents, the topics that we are going to see in the session is in magnetostatics. We are going to see about the Biot-Savart's law and how the equation is derived by using the four relations in Biot-Savart's law, and then we are going to see about the Hall effect and the applications that are there in Hall effect. Then coming to the electromagnetic induction, in electromagnetic induction we are going to see about the Faraday's laws, Faraday's first law and second law, and then we are going to see about the Lenz's law. Then we are going to see about what is self-inductance and mutual inductance. Okay, the first topic is related to the magnetostatics. In magnetostatics, the first one is Biot-Savart's law. Okay, according to A.H.D. experiment, A.H.D. proved that any current carrying coil will produce magnetic field around it. Okay? If the current is passing through a conductor, it will produce a magnetic field around it. Okay? In 1820, Biot and Savart, okay, the two scientists, Biot and Savart, performed many experiments, and they came to the study of magnetic field produced by various current carrying conductors. Okay, after many experiments, they obtained a relation by means of which the magnetic induction or the magnetic field B can be calculated at any point of space around a conductor in which the current is passing through it. Okay, if the current is passing through a conductor, the magnetic field B can be calculated around the conductor at any point, okay, around that conductor. They proved that this relation is called as the Biot-Savart's law. Okay. You can see here, this is the diagram that is related to a Biot-Savart's law. Okay, here AB is the conductor of length. Okay, AB is the length of a conductor, then DL is the element. Okay, and P is the point where the electric field B is to be calculated. The distance between the point P and element L, the electric element DL, is given by R. The distance between them is R, and theta is the angle between them. Okay. Now the current I is passing through this conductor. Now, according to Biot-Savart's law, the magnetic field or dB is directly proportional to I. Okay, magnetic induction is directly proportional to the current passing through the conductor. Similarly, the magnetic induction or the magnetic field is directly proportional to the length of the element dl. Okay, again the magnetic field or the magnetic intensity is directly proportional to the sine of angle between the point that is joining the point P and the length element dl, which is given by theta. Okay, dB directly proportional to sine theta, and the last one, dB is inversely proportional to the square of the distance between the length element and the point P, where the intensity is to be calculated, that is given by R. Okay, dB directly proportional to I, dB directly proportional to dl, dB directly proportional to sine theta, and dB directly proportional to 1 by R square. Okay, by merging all these relations, we can get a relation like dB directly proportional to I dl sine theta by R square, where I is the current that is passing through the conductor, dl is the length of the element dl, and theta is the angle between the point P and the length element dl, and R is the distance between them. Okay, dV is equal to mu naught by 4 pi I dl sine theta by R square, where mu naught is the permeability of free space. Okay, epsilon naught is the permittivity. Similarly, mu naught is the permeability in magnetostatics. Okay, mu naught by 4 pi is called as the proportionality constant, and mu naught is called as the permeability of free space. Okay. If you want the total magnetic field B, you can just integrate. Okay, integral dB. So B is equal to integral dB, and B is equal to integral mu naught by 4 pi ideal sin theta by r square. And as I said, mu naught by 4 pi is the proportionality constant, which is equal to the 4 pi into mu naught by 4 pi is equal to the 10 power minus 7 Weber per ampere meter. Okay, where I is the current that is passing through the conductor, and r is the distance between the length element and the point P. Okay. Next topic is about the Hall effect. Okay, what is meant coming to the introduction that we need before going to Hall effect is a phenomena where the voltage difference or the potential difference is created across a conductor transverse to the electric field when a magnetic field is applied. When the magnetic field is applied, the voltage difference is created across a conductor. Okay. This was discovered by Edwin Hall. Okay, as you know that Hall effect, it was discovered by the scientist Edwin Hall in 1879. Okay, it is a crucial concept in understanding the behavior of charge carriers in materials. Okay, what are the majority charge carriers, minority charge carriers, how they move. Okay, the Hall effect is widely used in various applications ranging from electronics to material science. It is widely used concept, Hall effect, and the applications are now coming to the principle of Hall effect. You can see in this diagram, when the magnetic field is applied perpendicular to the current carrying conductor. Okay, you can see the magnetic field is applied to the current carrying conductor. Potential difference is developed between the points on the opposite of the conductor. In perpendicular, a potential difference is applied. You can see by using this multimeter you can calculate the potential difference. Okay, this is called as the principle of Hall effect. The Hall voltage, which is represented by the letter VH, is directly proportional to the magnetic field strength, current, and Hall coefficient of the material. The Hall coefficient is given by the letter RH, R suffix H. Now, coming to the determination of Hall coefficient, Hall coefficient RH is a material specific parameter that quantifies the Hall effect in a given material. Okay, it determines the Hall effect in a given material. The Hall coefficient is experimentally determined by measuring the Hall voltage, current, magnetic field, and dimensions of the material. Okay. The ratio of Hall electric field. This is how we are going to determine the Hall coefficient. As you see here, what is Hall coefficient? The ratio of electric field, okay, the electric field, Hall electric field we can say, is given by the letter EH to the product of current density J. Magnetic induction B is known as the Hall coefficient. Okay, the Hall coefficient is represented by the letter RH. Okay. RH is equal to EH by JB, where RH is the Hall coefficient, EH is the Hall electric field, J is the current density, and B is called as the magnetic induction. So RH is equal to EH by JB. Okay, EH by JB is equal to 1 by N into Q, where N is the number of charge carriers and Q is the charge. The Hall coefficient can also be determined by using number of charge carriers and Q. It is given by the relation RH is equal to 1 by N into Q. This is how we are going to determine the Hall coefficient RH. Okay. Coming to the applications of Hall effect. Hall effect is used to determine the sign of the charge carriers. Okay, it is used to determine the sign of the charge carriers. It is also used to determine the density of charge carriers can be found in this effect. Okay, what is the density of charge carriers in a particular material, that is we are going to calculate. Okay, it can also be used to measure the drift velocity, which is given by VD. of charge carriers, the drift velocity of charge carriers, and it can also be used in understanding the electrical conditions in metals and semiconductors, how they are working electrical condition. By applying Hall effect, we are going to see, or you are going to understand in metals and semiconductors. Coming to the other concept, electromagnetic induction, Faraday's laws. The first topic is Faraday's laws. Faraday's laws are the fundamental principles of in electromagnetism. In order to understand the electromagnetism, you should know about the Faraday's laws. They describes, they tells us how a changing magnetic field induces an electric current. Okay? These laws are formulated by Michael Faraday in the 1830s. In 1830s, Faraday introduced these laws. So coming to the Faraday's first law, you can see here, when the magnetic flux linked with the circuit is changed. Okay, as you know that by Oersted experiment, any charge carrying conductor will produce magnetic field around it. When the magnetic flux linked within the circuit is changed, an EMF, an electromotive force, is induced in the circuit, okay, which is known as Faraday's first law. Okay. When there is a change in the magnetic flux linked with the circuit, an induced EMF is produced in the circuit. Simply you can say like this. Okay. Coming to the Faraday's second law, the magnitudes of induced EMF, or the magnitude of induced electromotive force, is directly proportional to the negative rate of variation of magnetic flux linked with the circuit. Okay. Induced EMF, which is given by letter E, is equal to the minus d phi by dt, or you can say E is equal to minus d phi b by dt. Phi b is called as the you can say magnetic flux that is linked to the conductor. Magnetic flux that is linked to the conductor. Okay, E is equal to minus d phi by dt, or you can say that E is equal to minus n into d phi by dt, where n is the number of turns in the coil, and E is called as the electromotive force, and d phi by dt is the instantaneous change, or you can say that the rate of change of magnetic flux linked to the circuit. Okay, this is called as the Faraday's second law. Coming to the Lenz law, Lenz law is the consequence of Faraday's law. Okay, it states that the direction of the induced EMF or the current creates in a closed circuit is such that it opposes the original cause that produces it. Okay, it opposes the original cause that produces it. This law ensures that the energy is conserved in electromagnetic process. Okay, we can say that the energy is conserved in electromagnetic process. Now coming to the inductance, there we have two types of inductance: self-inductance and mutual inductance. Okay. Inductance is a property of a conductor by which a change in current flowing through it induces an electromotive force EMF in itself is as well as in neighboring conductors. Okay. It is a measure of it. We know that the inductance is measured in Henry, and it is crucial in functioning of the electrical circuits. Okay. Self-inductance and mutual inductance are two key aspects of the inductance. Coming to the first one, self-inductance. Self-inductance is the phenomena where a changing current, induces an EMF in the same circuit. Okay, induces an EMF in the same circuit. The coefficient of self-inductance is denoted by the letter L. Okay, the coefficient of self-inductance is given by the letter L, and it is a measure of how much EMF is induced in the circuit. Okay. Self-inductance opposes any change in the current flowing through the circuit. Okay. It opposes any change in the current flowing through the circuit. Coming to the mutual inductance occurs when the change in current in one circuit induces an EMF in the adjacent circuit. Okay. Mutual inductance is observed in transformers as well. You can see in this diagram. As you know that there are two types of transformers: step up and step down transformer based on the number of terms in the primary and secondary coil. The coefficient of mutual inductance is denoted by letter M. As you know that self-inductance, coefficient of self-inductance is represented by letter L. The coefficient of self-inductance is determined the letter M. It quantifies the extent of EMF induced in the neighboring circuit during the change in current in the other circuit. Okay. Mutual inductance is the basis for the transformers and other devices that transfers energy wirelessly.